So hello everyone, today's lecture will be about ZK SNARKs. So in our lecture series we have seen ZK rollups where a ZK proof is submitted on chain. So in this session we will see how the proof is generated and verified. So ZK SNARKs are a way to prove that you know something without revealing the information itself. So they allow one party to prove to another that a statement is true without showing any details about the statement. So the following components form the ZK SNARKs. It is zero knowledge, it is succinct, it is non-interactive, and it provides argument of knowledge. So zero knowledge means nothing is revealed other than a truth of statement, and succinct means that our proof is concise. Uh, like the size of the proof is not very big, and it can be verified quickly. Non-interactive. So there are two ways to approach a ZK proof. One is interactive and one is non-interactive. So in interactive proofs, a series of question and answer is there. Uh, Verifier asks prover some kind of information and the prover replies back, and the verifier again asks some counter question. But in non-interactive proof, the proof is like in a stored version. So verifier can anytime check the validity of the proof. Okay, and argument of knowledge. The prover provides the verifier with the argument that yes, he knows some information. So how are they implemented? There are mainly five steps: arithmetization, R1CS, R1CS to QAP, encryption of QAP, and shifting salting. And we'll go through each of them one by one. So first is arithmetization. So uh, user if a user wants to prove some information that he has, so he has to represent the information in some sort of like mathematical equation. So let's say he represented his information in the form out equal to y squared plus 4x square y minus 2. Okay, so now we will apply arithmetization on it. So arithmetization is nothing but breaking down this mathematical equation into simpler steps. Okay, like you can see there are many operations in this single equation. Like there are x square y, there are three variables multiplication here. In y square is also then variable multiplication, and then these are added. So in arithmetization we decompose this statement into like simpler steps. Okay, so what's the rule? The rule is simple: one line, one operation. That means in one line you can have only at most one uh, non-scalar multiplication. Non-scalar multiplication means the multiplication between two variables. So such as like 5 into y is not a uh, it is a scalar multiplication. So like that can be accommodated, multiple scalar multiplication can be accommodated in one line, but for a non-scalar you have to take only one line. Okay, so this is my equation, and I have broken down into three constraints. So in order to do this, I have introduced two intermediate variables v1 and v2, and this is exactly the same equation as above. So one more thing, like in your in expressing your information, there can be some operations like comparators and some other operations like bitwise. But the rule here is that you want to represent your equation in terms of only addition and subtraction. Okay, so if you have an operation like bitwise, like left shift and right shift, so you have to convert it into um, addition and multiplication. So suppose one left shift 2, you can easily convert it into multiplication using like one left shift 2 is equivalent to multiplying it with 2 to the power 2, which is 4. So like there are other tricks to convert the comparators operation to the addition and subtraction. We will not go into that. So we now have our computation expressed as a sequence of constraint. So we will take it one step further and make another transformation that describes the equation like in a different format, and that format is R1CS. our rank 1 constraint system. Okay, so for this we will introduce a witness vector. Witness vector is a vector of dimension 1 into n, which is a solution of the constraint. Okay, so like this was my constraint. A witness vector is a vector that will have the values that will satisfy these constraints. So uh, its dimension is 1 into n, and n is number of variables plus 1. This number of variables include all the variables, whether it is input, output, or intermediate. So this is the structure of our witness vector. And you can see there is a extra one here. So like, what's the importance of one? It facilitates free addition. And how's that? I will come to that later. So for this set of constraint, the witness vector is this. So this means that for x equal to 3 and y equal to 4 and out equal to 199, it is a solution of our regional equation. So, so our aim is to calculate these matrices A, B, and C. Uh, so A, B, and so A, B, and C are matrices that we use to convert uh, this equation into R1CS. So what are the dimension of ABC? These are n into m, n rows, and sorry it is misprinted, n rows and m columns. So n is the number of constraint. So like in this example, we have total number of constraint equal to 3, and m is equal to the number of witness elements. So we have seen number of witness element was number of variables and 1. So here if you count that 1, 2, 3, 4, and 5. So 5 variables and plus 1 for the 1. And so the number of columns are 6. Now how to calculate this matrices A, B, and C? So these are our final matrices A, B, and C. So like if you we have 3 rows here. First so the first row, second row, and the third row. The first row, when you multiply all the first row elements with the witness vector, this will generate the first constraint. And similarly we can do that for second and third. So like you can see, if you do the simple matrix multiplication here, the one is multiplied with v1, and here the one is multiplied with y, and here one is with y. So this will become v1 equal to y square, and this is essentially our first constraint. Okay, so let's say how we can convert this second constraint into the vector form. So we have v2 here. Okay, and the v2 position in the witness vector is the last. So in the matrix C, the second row of that will only have one at the last position of it, that is v2, and all the elements will be 0. Let's check it. Yes, it's true. You can see there's only a single one here, and rest of the all elements are 0. And for A we have x here, and for B we also have an x here. So x is the third element in the witness vector, so we will have a 1 here, and rest all of the elements are 0. So you can check it. uh, Now I will explain the importance of 1. So there's a general saying in the ZK that addition is free. What does that mean? So like you can see here, uh, there is a already a variable multiplication here, and I said that only one line can have only one variable multiplication, but along with that we have a v1 and -2 here. So how we can accommodate it in our R1CS? So let's shift v1 and -2 to the left hand side. Okay, so and so let's expand expand when the third row will be multiplied with the witness vector. So we will have a 2 into 1 plus 1 into out plus 0x plus 0y minus v1. And you can see all the terms are separated by addition because of the property of matrix multiplication. And that's why like we can accommodate as many addition as we want. So for variable addition, we can mark the corresponding coefficient like whatever the coefficient here is in these entries, and if the so now I will tell you the importance of one. Suppose there is a constant addition, like in this the -2. So there there has to be a value which represent the constant value in our constraint system. So like the 2 will be multiplied with a 1 here, and that's consistent with the equation here. So actually it is not exactly written correct. It's facilitates addition of it's facilitates free addition of constant, but variable we can do without one also. So this I have already covered. So the next step is R1CS to QFP. QFP stands for Quadratic Arithmetic Program. So we have transformed our equation to R1CS. Now we need another transformation, that is QFP. So let's talk about what's the need for this transformation. See, the proof generated by R1CS is not succinct. We want it to be clear and precise. Okay, you can see there are lot of zero multiplication, and that is not adding up anything to our final constraint. Okay, so that's a waste of time complexity and also space complexity. So, and that's the reason this conversion is there, because QAP are the reason the ZK SNARKs are succinct. Okay, so we condense matrix to a single polynomial expression using Lagrange interpolation. So what is it? I will come to that later. So at the end of R1CS, we got CW equal to AW into BW, where CAB are my matrices. So we will convert it into this part. WA equal to UA into VA. This represent the a polynomial expression. So So now let me explain you what is Lagrange interpolation. So like suppose we have these 3 points 1 comma 0, 2 comma 1 and 3 comma 0. Uh, Lagrange interpolation says that we can uniquely determine a 2-degree polynomial passing through these 3 points. So that is easy. Like you can write the general form of 2-degree polynomial ax square plus bx plus c, and just substitute the value of y and x, and you will get a, b and c. So generalizing it, if you have endpoints, if you are given endpoints, then you can uniquely determine a polynomial equation with a degree of n minus 1. So that is Lagrange interpolation. So my aim is to convert the A, B, C matrices into the polynomial expression. So let's say the polynomial expression we are taking is in the variable x. So for and now let's make another assumption that this is not an assumption, sorry, that the first row correspond to the x equal to 1, the second row correspond to x equal to 2, and third row correspond to x equal to 3. So what does that mean? I am explaining. So let's say for each of the matrices A, B, and C, and in each matrix for each of the elements in the witness vector, we will have a separate polynomial. So like this is our matrix A that we generated in the R1CS. Okay, so like there these are the entries of x 0 1 0. So there will be a separate uh, polynomial only dedicated to x. So as I said that the first row correspond to the x equal to 1, and the second x equal to 1, and third x equal to 3. So just take the point 1 comma 0, 2 comma 1 and 3 comma 0, and you will get the equation minus x squared plus 4x minus 3. And you will do for each of the element, for each of the columns. So like substitute, take 3 points 1 comma 1, 2 comma 0 and 3 comma 0, you will get this polynomial. And similarly do that for v2. You can ignore the 0 columns here because they effectively give you the 0 polynomial, like you don't need to calculate it. So after after calculating it, you will get this final expression. So this is my corresponding expression for the matrix A in the QFP. So Now I will explain that what does that x first row means x equal to 1. That mean let put x equal to 1 in this equation. So when we put x equal to 1 in this equation, and the purple matrix will come out to be 0, and similarly you can see the pink matrix will also come out to be 0. And when you will put x equal to 1 here, then sorry, it is misprinted. It is 0.5 x square minus 2.5 x. So you will see that if x equal to 1 is put here, then you will get 1 from here. And so effectively when we put x equal to 1 in this, we get 0x plus 1y plus 0v2, which means we get a y. So this was my matrix A. And let's come back to the original constraint system, and you can see that the variable corresponding to the A matrix was y. So that's consistent with the R1CS. So similarly, if you will put x equal to 2 in this equation, you will get the final expression equal to x. So this was a witness vector that only the prover has. So he will substitute the value of x, y, and v2 in this and generate a final expression for the matrix A. And similarly, this operation is applied on matrix B and C, and you will get finally 3 polynomials A, B, and C. So now we got this polynomial A, B, and C, which is also WA, UA, and VA. And if you can see that they are not balancing. Like the degree of the polynomial on the right hand side is 4, and the degree on the left hand side is 2. Although on the values of x equal to 1, 2, 3, which means like the number of the constraint numbers, their values are equal. Like I have calculated it for the x equal to 1, the right hand side comes out to be 9 and left hand side also come out to be 9. You can also verify that for x equal to 1, 2, and 3, their values are same, but the polynomials are not equal. But for the sake of zero knowledge, we want that the polynomials are all same. So how we can achieve that? So this we can achieve that with the help of division theorem. So we will divide our polynomial UA into VA, which is of degree 4, with another polynomial TX that will give you a quotient HX plus a remainder WA. This is like consistent with the polynomial division theorem which we have studied. Like Px equal any polynomial Px can be represented as Qx into Hx plus Rx. So now question is what would be the choice of Tx? So in the ZK SNARKs, Tx is chosen to be as x minus 1, x minus 2, x minus till x minus number of constraint. So for our example, it would be equal to x minus 1 into x minus 2 into x minus 3. And now the question is, why this Tx? Uh, there are mainly two reasons. The first is like this Tx is publicly known to both the prover and the verifier. So it prevents the prover to forge the proof of the information. Like now he cannot just randomly pick up 4 polynomials px, qx, rx, and hx and ensure that the polynomial division theorem is satisfied on it and provide it to the verifier. Now the tx is fixed, so verifier can easily check that yes, it is the tx that we agreed upon. And the second reason is you can see that yes, I have already stated that the value of UA into VA and WA are equal at x equal to 1, 2, and 3. So this numerator will come out to be 0 of for x equal to 1, 2, and 3. So so basically Tx is just a factor of the numerator. So it will give you a perfect remainder, perfect quotient. Sorry. Okay, so so far we have generated the final QA, final polynomial expressions. Now we have to encrypt them. So I will explain you the need of the encryption. So this was the polynomial expression for A that we generated. So let's say the prover provided directly to the verifier. Okay, and uh, at till this step, the prover and verifier both have the same information. Like the prover verifier knows what are the set of constraints that the prover wants to prove. So he can also verifier can also reach till this point. So after this point, the prover provides the verifier with this information, and verifier can now make an equation into x, y, and v2, like how he can just compare the coefficient of x in this and in this expression. So like if he compares the coefficient of x to the power 2, it will give us minus x. This was plus zero point 0.5 as I mentioned earlier. So minus x plus 0.5 y plus 2v2 equal to 29.5. So this will give me one equation, and similarly two more equations will be generated for x to the power 1 and x to the power 0. So this is three equations in three variables. So verifier can easily solve it and can get the values of x, y, and v2. So that's the reason we have to encrypt this information of the polynomials. So we need to encrypt the polynomials to a homomorphic space using one-way mapping. And now I will explain you the meaning of the terms mentioned in this definition. Homomorphic means that there is a correspondence between two algebraic systems. Like let's say we have algebraic system, like the normal algebraic system we are used to, like the 1 is 1 and 2 is 2, and we are mapping all the values in it to a new algebraic system as to the power a. So we can pick whatever the s is, like suppose we pick as equal to 2, so now 2 will become 4 and 3 will become 8. So this is homomorphic, that there's a correspondence between two algebraic system. That this means that if I apply an operation on the first system, like if I apply a plus b, addition operation on two variables on the first system, then this will correspond to another operation in uh, the second algebraic system, and that can be anything, that can be like customly defined also. So in this example, the plus operator will be matched to the multiplication. And using one way mapping is that we can't, if we have the encrypted number, we can't tell what was the number it was generated from. That's the meaning of one way. So like this, let's come to the example. Take s equal to 2. Now suppose this s equal to 2 is known to both prover and the verifier, and a equal to 3. So this is a equal to 3 is mapped to 8. Now you will question that, okay, I know s equal to 2, I know the mapping is 8, I know how the things were mapped. So I can just easily, like I can take the log of 8 and tell what was the original value. So log of 8 will be 3, and yes, I got the value in the first algebraic system. So how it is one way? So modulus to the rescue. So we will calculate every encryption modulo some prime number p. So let's say after uh, calculating s to the power a, we are also doing it modulus with the number 7. So 8 will become 1. 8 mod 7 equal to 1. So now I am a prover, and s equal to 2 is known to both prover and the verifier, and a equal to 3 is already all only known to me. So after mapping it to the encrypted space, which comes out to be 8 mod 7 equal to 1, I gave it to the verifier. So verifier, what the, what information does the verifier have? He knows s equal to 2, he knows the mapped value is 1. Can he guess a equal to 3? No, because simply uh, there can be a many possibilities, because 2 cube mod 7 equal to 1, and 2 to the power 6, which is 64. When you take the mod of 64 with 7, it also comes out to be 1. So now the verifier can't tell what was the pre-image of the encrypted message. Okay, so this was one sort of encryption, but in the ZK SNARKs, elliptic curve cryptography is used to encrypt the polynomials. So for those who don't know the elliptic curves, I will brief you about them. So they are used to define robust collision resistant and one-way function that are used to map the polynomials generated after the QAP. So we have some set of polynomials that we have after the QAP process, and now we want to encrypt them. So for that, elliptic curves is used. So they are defined over a finite field. This means that uh, they are not defined over like a very large number. The number can goes to till infinity. Um, we are already we are only we are only concerned about a limited set of numbers, and for example we can take only 0 to p minus 1 number where p is a prime number. uh, they are cyclic. So what does that mean? I will explain you with an analogy. So we have a set here, 0 1 2 till p minus 1. It is also a finite field, just like I explained here. So uh, if I have to done addition modulus in this uh, on this finite field, okay, so you can see that uh, it is cyclic because if I choose a generated element 1, so first of all, what does cyclic mean? Cyclic means if I take a element from the set and apply the operation defined on that set repeatedly, then I can generate all the elements the possible in the set. So like in this set, the generated element is 1 because like 1 plus 1 is 2, and 1 plus 1 plus 1 is 3, and I can apply addition on 1 like several times to generate every element possible. And how 0 can be generated from 1? I can just add 1 p times, so this will gives you a 0. And when you add 1 p plus 1 times, this will again come back to 1. So this is cyclic. So just like how addition modulo was a cyclic group, elliptic curves are also cyclic. This means that there exists a generator element on which if you repeatedly apply operation, it's not necessary that it it, it can addition, it can be anything. In this case, this is point addition. So if you repeatedly apply point addition to the elliptic curves to the generated element g, you can get every possible element. So like g plus d equal to 2g, and so on, you can generate every element possible. For some r into g equal to 0. So one thing to note that here the plus sign doesn't mean that it is the actual addition, it is point addition. Like it is some kind of operation that is defined specifically for elliptic curves. You don't need to know the how implementation of it for the sake of lecture. You can just remember in this lecture that they are just a simple plus sign. So so let's talk about the discrete logarithmic theorem. It's a very important theorem with respect to the elliptic curve. So this tells you that if you know elliptical point x into g, which was formed by repeatedly applying the binary operation on g. So you cannot infer what was the value of x from it. So just as an example, if you know a point 0.5 in a domain, and if you apply the operation on the generated element g 5 times, you will get 5 into g. So this is what exactly it means, that if you have a variable x and if you encrypt it to the value x into g, you cannot tell what was the x if you destroy it after the encryption. So let's understand it with uh, our previous analogy. So this was equivalent to the analogy I discussed earlier, like you cannot like in this encryption we were not able to tell that a equal to a was 3 or 6. So this is also exactly, it also worked like this. So that was all about elliptical curve. This will be enough to understand how the QAP are encrypted. So at the end of my QAP process, quadratic arithmetic process, I got some set of polynomials, and this equation was generated after the QAP. This was a question, just it is rearranged. Tx is multiplied here and w is brought to the left hand side. So now I want to encrypt it in the elliptical curve field. So just remember for this lecture that whenever a variable has a square brackets around it, this means that it is a elliptical curve point. So the UA polynomial will be encrypted to A, and the VA polynomial is encrypted to B, and similarly they are W is encrypted to C, and HXTS is encrypted to HT. So this statement is equivalent to A into B equal to C plus H2, C plus HT. So how the encryption is done? In a trusted setup, it's a third party setup. A secret key tau is picked and powers of tau is calculated. So whatever was the degree of this polynomial, up to that power, the powers of tau is calculated. So we will calculate tau 0, tau 1 and tau 2 encrypted to the G. And because of the discrete logarithmic theorem we discussed, if we have these points after we generate them, and if we destroy the tau after generating them, we cannot tell what was the tau here. So now here's the question. So why prover is not allowed to pick that secret key tau? Mm. Uh, Before that, if you are confused, the tau is nothing but the value. Tau is nothing but a value of x. We can put x equal to tau. We are putting x equal to tau here, and that is encrypting. So like it will be forming tau square tau. So it is encrypted to this set of elliptic points. So why the prover is not allowed to pick tau? Why the third party is picking up tau? Because if the prover was allowed to pick tau, then he can forge the proof. Like he can generate like he can generate any elliptical point such that they satisfy it. A B such that they satisfy this constraint A B equal to C plus HT, and it's not difficult. And so the verifier will doesn't know that this elliptical curve points came from the QFP or just randomly generated. So that's the reason the secret key tau is picked up by the trusted setup, not the prover. Similarly, we can encrypt the polynomial V and WA, and that results us into the polynomial elliptical points B and D. And similarly, the encryption of polynomial Tx and Hx is done, and after that Hx encryption of Hx into Tx is done, and that will give us a point Ht. So finally we want to prove the verify this equality A B equal to D plus Ht. So let's say C equal to D plus Ht. So the prover will then provide these values A, B, and C to the verifier, and the verifier will then check if the pairing of AB is equal to the pairing of C with the point G2. You will be like confused that from where does this point G2 came. So the thing is that the point the point A is generated. Uh, the point A and B are generated in different groups. Like they are elliptical curves, but they are part of like separate elliptical curves. So let's the A is a point of a G1 group, and the B is a point of G2 group. and the D is the point of G1 group. So you can also see here the A is G1 and and for the encryption of VA we have used a G2 here, and that's the reason we were using these two set of encrypted points. And for the sake of this lecture, just remember that the pairing of G1 and G2 gives you another point that is in another ring, that is G12. So this is like the 1 and 2. There are two groups, G1 and G2, and they gives you a point in another field, in another algebraic field. So when the pairing of A1 and B2 is done, you get a point of G12, and you can't just directly equate this to the C1 because they are then they will be a member of two different groups. So that's why we paired it with a G2, so that here pairing of 1 and 2 will also result into a G12. So on both sides we are comparing G12 member groups or group members. So this was like a very high level knowledge about. You can just remember that we are only doing A B equal to C. So what are the problems in it? uh, the prover can simply invent values where C equal to AB, and then uh, encrypt them, and then provide this to the verifier, and the verifier will check C equal to A into B. So for this some modifications are there, shifting salting. So in 2016, a person named Growth proposed this modification. That's why like this was the Growth 16 algorithm. So that rusted, we have seen that the rusted setup was encrypting a secret key tau, and uh, that trusted setup also pick two points alpha and beta, and encrypt them big, uh, to form points alpha G1 and beta G2. So now after encrypting them, he will uh, throw the alpha and beta, just destroy them, so that one can never be able to uh, find the pre-image of these two elliptical points, and he will give these 2 points alpha G and beta G to both the prover and verifier. So how does the prover will use them? So the prover will updates their A and B elliptical points by adding alpha G and beta G to respective A and B, and this will give prover the updated A and B points. So like this was the equation A into B equal to C plus HT. So when the addition of salt is done, alpha comma beta, uh, alpha is added to U is equivalent to elliptical point A, and V is equivalent to elliptical point B. So when alpha and beta are added to this, then the final equation generated is this, and this has to be verified by the verifier. So these underlying parts are calculated by prover, and they will form the ABC endpoint, and the prover will provide the A, B, and C points to the verifier. And there's an extra alpha beta term here. Alpha beta is the pairing of alpha G1 and beta G2, and it's again a G12 point. Okay, so it's consistent with all. Um, it's consistent with all we will do. Like we will do the pairing of A B, that will give you a G12 point. So alpha beta is also G12, so it's consistent. So prover will calculate A, B, and C and will provide it to the verifier. And earlier I mentioned that alpha G and beta G are provided to both the prover and verifier. The prover, we have seen that how the prover is using them to update the points A and B. The verifier uses them in the verifying stage. That's how he calculate this pairing alpha and alpha beta. If he has alpha G1 and beta G2, and simply he calculate the pairing alongside when he is calculating the pairing of AB and CG. So this was all about the lecture. In this lecture, we have seen about SNARKs and growth 16. In the upcoming lecture, we will see about the Plonkish arithmetization. Thank you.